Friends, in this module we will derive the identities based on sum and difference of angles of trigonometric functions and use them in deriving some identities based on them. We will first prove the identity cos of x plus y is equal to cos x cos y minus sin x sin y. Using this, we will derive other formulae relating sum and difference of two angles. Sine and cosine functions of sum and difference of two angles. In this section, we shall derive expressions for trigonometric functions of the sum and difference of two numbers, angles and related expressions. The basic results in this connection are called trigonometric identities. We have already seen that sine of minus x is equal to minus times sin x and cos of minus x remains cos x only. We shall now prove some more results. First, cos of x plus y is equal to cos x cos y minus sin x sin y. Consider a unit circle with the center at origin. Let x be the angle P4 OP1 and y be the angle P1 OP2. Then x plus y is the angle P4 OP2. Also, let minus y be the angle P4 OP3. Therefore, P1, P2 and P3 and P4 will have the coordinates P1 cos x sin x, P2 will be having the coordinates cos of x plus y sin of x plus y, P3 will have coordinates cos of minus y sin of minus y and P4 will have the coordinates 1 0. Consider the triangles P1OP3 and P2OP4. They are congruent by SAS property. Therefore, P1P3 and P2P4 are equal. By using the distance formula, we get P1P3 the whole square is equal to cos x minus cos of minus y the whole square plus sin x minus sin of minus y the whole square, which is equal to cos x minus cos y, because cos of minus y is cos y the whole square, plus sin x plus sin y the whole square, because sin of minus y is minus sin y. Now, on opening the brackets, we get cos square x plus cos square y minus 2 times cos x cos y plus sin square x plus sin square y plus 2 times sin x into sin y. Now, replacing cos square x plus sin square x by 1 and cos square y plus sin square y by 1, we get this as P1 P3 the whole square is equal to 2 minus 2 times cos x cos y minus sin x sin y. Now, let us take P2 P4 the whole square, which is equal to 1 minus cos x plus y the whole square plus 0 minus sin x plus y the whole square. On expanding, this comes out to be equal to 1 plus cos square x plus y minus 2 times cos of x plus y plus sin square x plus y. We again replace cos square x plus y plus sin square x plus y by 1, which gives the value of P2 P4 the whole square as 2 minus 2 times cos of x plus y. Now, we have already stated that P1 P3 is equal to P2 P4. Therefore, P1 P3 the whole square is equal to P2 P4 the whole square. Therefore, 2 minus 2 times cos x cos y minus sin x and y is equal to 2 minus 2 times cos of x plus y. Now comparing the two sides, we get cos of x plus y is equal to cos x cos y minus sin x sin y. Friends, now we will see how do we get the formula for cos of x minus y. In the identity which we have proved, we will replace y by minus y. On replacing y by minus y, we get cos of x plus minus y is equal to cos x cos of minus y minus times sin x into sin of minus y. Now again we will apply cos of minus y is cos of y, sin of minus y is minus times sin y. Therefore, we get cos of x minus y is equal to cos x cos y plus sin x sin y. Next, let us see how cos of pi by 2 minus x is equal to sin x. We will replace x by pi by 2 and y by x in our identity 4 which we have just now derived. We get cos of pi by 2 minus x is equal to cos pi by 2 into cos x plus sin pi by 2 into sin x. Since value of cos pi by 2 is 0, therefore, cos of pi by 2 minus x is equal to sin of x. In sixth identity, we will prove that sin of pi by 2 minus x is equal to cos of x. We will use our identity 5 and we will replace this sin of pi by 2 minus x as cos of pi by 2 minus pi by 2 minus x, which gives us the result as cos x because pi by 2 cancels with minus pi by 2. Let us now try to find out the identity for sin of x plus y. We know that sin of x plus y can be written as cos of pi by 2 minus times x plus y, or we can rearrange this as cos of pi by 2 minus x minus y. We will apply the identity of cos of x minus y, which gives the value as cos of pi by 2 minus x cos y plus sin of pi by 2 minus x sin y. Now, cos of pi by 2 minus x can be replaced by sin x and sin of pi by 2 minus x can be replaced by cos x. So, we can say that sin of x plus y is equal to sin x cos y plus cos x sin y. Let us see what happens if it is sin of x minus y. In sin of x minus y, what we do is to get this result, we will replace y in identity 7 by minus y. We get result. Now, by taking suitable values of x and y in the identities 3, 4, 7 and 8, we get the following results. Cos of pi by 2 plus x is equal to minus sin x, whereas sin of pi by 2 plus x is equal to cos x. Cos of pi minus x is equal to minus times cos x, but sin of pi minus x remains sin x. Cos of pi plus x becomes minus cos x because pi by x is in the third quadrant. Also, sin of pi plus x is equal to minus sin x. Cos of 2 pi minus x is equal to cos x because 2 pi minus x is in the fourth quadrant. Therefore, sin of 2 pi minus x becomes minus times sin x. Now, let us solve some examples. Example 1, if sin A is 3 by 5 and A lies between 0 to pi by 2 and cos B is minus 12 by 13, when B lies between pi to 3 by 2, we will find the value of sin A minus B. Sin A is 3 by 5 and A lies between 0 to pi by 2, that is in the first quadrant. Therefore, cos A will be positive and its value will be 4 by 5. Cos B is minus times 12 by 13. B lies between pi to 3 pi by 2, that is in the third quadrant. Therefore, sin B will be minus 5 by 13. Putting these values in the formula for sin of A minus B, which is equal to sin A cos B minus cos A sin B, we get sin A is 3 by 5 into cos B, which is minus 12 by 13, minus 4 by 5, which is value of cos A, into minus 5 by 13, the value of sin B. On simplification, the value of sin A minus B comes out to be minus 16 by 65. In example 2, we take the value of sin A as 3 by 5, cos B as minus 12 by 13. Now, we will try to find out the value of cos of A plus B. Now, sin A is 3 by 5 and A lies from 0 to pi by 2, therefore, cos A is 4 by 5. Cos B is minus 12 by 13, but B lies in the third quadrant. Therefore, sin B is minus 5 by 13. Cos of A plus B can be written as cos A cos B minus sin A sin B. Value of cos A is 4 by 5, value of cos B is minus 12 by 13, which we substitute, minus times value of sin A 3 by 5 and value of sin B, which is minus 5 by 13, is being placed in their respective places. On simplification, value of cos of A plus B comes out to be minus 33 upon 65. In example 3, we will find out the value of sin 75 degrees and cos 75 degrees. To begin with, sin 75 degrees can be written as sin of 45 degree plus 30 degree. Now, using the formula for sin of 45 degree plus 30 degree can be written as sin 45 degree cos 30 degree plus cos 45 degree sin 30 degree. Value of sin 45 is 1 by root 2, value of cos 30 degree is root 3 by 2 plus value of cos 45 degree is 1 by root 2 and value of sin 30 degree is 1 by 2. When we simplify this expression, value of sin 75 degree is root 3 plus 1 upon 2 root 2. Similarly, cos of 75 degrees is equal to cos 45 plus 30 degree, which is cos 45 degree cos 30 degree minus sin 45 degree into sin 30 degree. Again, replacing cos 45 degree as 1 by root 2, cos 30 degree as root 3 by 2 minus sin 45 degree as 1 by root 2 and sin 30 degree as 1 by 2, on simplification gives the value of cos 75 degree as root 3 minus 1 divided by 2 root 2. In example 4, we will evaluate cos 2 pi by 3 into cos pi by 4 minus sin 2 pi by 3 into sin pi by 4. Now, cos 2 pi by 3 into cos pi by 4 minus sin 2 pi by 3 into sin pi by 4 can be written as cos of 2 pi by 3 plus pi by 4, which is equal to cos of 11 pi by 12. On converting 11 pi by 12 into degrees, this comes out to be cos of 165 degree, which is equal to minus cos of 15 degree. Now, we will find out the value of cos of 15 degree. Cos 15 degree can be written as cos of 45 degree minus 30 degree, which is equal to cos 45 degree into cos 30 degree minus sin 45 degree into sin 30 degree. When we substitute the values, this comes out to be root 3 plus 1 upon 2 root 2. So, value of cos of 15 degrees is equal to root 3 plus 1 upon 2 root 2. But the answer is minus times cos of 15 degree. So, the given expression is equal to minus root 3 plus 1 upon 2 root 2. Now, we will take the tangent and cotangent functions of sum and difference of two angles. Similar results for tan x, cot x, sec x and cosec x can be obtained from the results of sin x and cos x. Next identity, if none of the angles x, y and x plus y is an odd multiple of pi by 2, then tan of x plus y can be written as tan x plus tan y upon 1 minus tan x into tan y. Since none of the x, y and x plus y is an odd multiple of pi by 2, it follows that cos x, cos y and cos of x plus y are non-zero. Now, tan of x plus y can be expressed as sin of x plus y divided by cos of x plus y. We know the formula for these two identities. So, tan of x plus y can further be expressed as sin x cos y plus cos x sin y divided by cos x cos y minus sin x sin y. Now, dividing the numerator and denominator both by cos x cos y, we have tan of x plus y can further be expressed as sin x cos y divided by cos x cos y plus cos x sin y divided by cos x into cos y. In the denominator, cos x cos y is divided by cos x cos y minus sin x sin y divided by cos x into cos y. On simplification, we get the identity tan of x plus y is equal to tan x plus tan y upon 1 minus tan x into tan y. Now, to get the identity for tan of x minus y, we replace y in identity 10 by minus y. We get tan of x minus y is tan of x plus minus y, which gives the result as tan of x minus y is equal to tan x minus tan y divided by 1 plus tan x tan y. For next, if none of the angles x, y and x plus y are multiple of pi, then cot of x plus y can be expressed as cot y cot x minus 1 upon cot y minus cot x. Since none of the x, y and x plus y is a multiple of pi, we find that sin x, sin y and sin of x plus y are non-zero. Now, cot of x plus y can further be expressed as cos of x plus y divided by sin of x plus y. And using the identities for cos of x plus y and sin of x plus y, cot of x plus y can be written as cos x cos y minus sin x sin y divided by sin x cos y plus cos x sin y. Dividing numerator and denominator by sin x sin y, we get cot of x plus y is equal to cot y cot x minus 1 divided by cot y plus cot of x. Now, for cot of x minus y, if none of the angles x, y and x minus y is a multiple of pi, then we replace y by minus y in our identity number 12 and we get the result cot of x minus y is equal to cot y cot x plus 1 upon cot y minus cot x. In example 5, we are going to use these identities. Now, we will evaluate tan of 15 degrees. Tan of 15 degrees can be written as tan of 45 degree minus 30 degree, which using the identity is equal to tan 45 degree minus tan 30 degree divided by 1 plus tan 45 degree into tan of 30 degree. Value of tan 30 degree is 1 by root 3 and value of tan 45 degree is 1. So, replacing these values by 1 and 1 by root 3, value of tan 15 degrees is 1 minus 1 by root 3 divided by 1 plus 1 by root 3. On taking the LCM, this comes out to be root 3 minus 1 upon root 3 plus 1. In example 6, we will show that tan 3x into tan 2x into tan x can be written as tan of 3x minus tan of 2x minus tan x. For this, friends, we start with taking 3x as 2x plus x. Now we will take tan of both the sides. So, tan 3x is equal to tan of 2x plus x. Tan of 2x plus x using the formula for tan of x plus y can be written as tan 2x plus tan x divided by 1 minus tan of 2x into tan of x. So, on cross multiplication we get tan 3x minus tan 3x into tan 2x into tan of x is equal to tan of 2x plus tan of x. Now, we will transpose the quantities from one side to the other, which will give the result as tan 3x minus tan 2x minus tan of x is equal to tan 3x tan 2x into tan of x, which can further be expressed as tan 3x into tan 2x into tan x can be written as tan of 3x minus tan of 2x minus tan x. Students, in example 7, if a plus b is pi by 4, we will prove that 1 plus tan a into 1 plus tan b is equal to 2. We have a plus b is equal to pi by 4. Taking tan of both the sides, tan of a plus b is equal to tan of pi by 4. Now, tan of a plus b can be expressed as tan a plus tan b upon 1 minus tan a into tan b, and our right hand side is tan of pi by 4, which is equal to 1. We will now cross multiply and we get tan a plus tan b is equal to 1 minus tan a into tan b. We rearrange the terms and we get tan a plus tan b plus tan of a into tan of b is 1. We add 1 to both the sides. So, 1 plus tan a plus tan b plus tan of a into b is equal to 2. Now, from the third and the fourth term, we take out tan b common and simplify. We get 1 plus tan a into 1 plus tan b is equal to 2. So, friends, in this module, identities based on trigonometric functions of sum and difference of two angles have been discussed. These identities have been used to solve various questions.